Hello, viewer. Greetings. I'm just waiting for a couple more viewers to show up. Greetings. I'm sleepy today. I'm finding that Thursdays are the most challenging days to wake up with this schedule. Hello, Geography Genius. I would say hi to all of you individually, but I don't want to say your name in the video because I'm posting it publicly. I could get in trouble. Boy, people are slow to join today. I'm about to just go for it. Yo, yo, yo. Dum-de-dum. Okay, I think people are rolling in now, so I'm going to start. So in the last lesson, we discussed what is a force, how do we calculate net force. If you have a two-dimensional forces, how do you calculate net force? And then we discussed Newton's laws of motion. So what we're going to do today is we're going to talk about some of the specific types of forces that we encounter. So I just called the forces F without saying where does the force come from, what is causing that force. But today we'll talk about some of the specific types that you might encounter. So some of this will be review. And then at the end of the lesson, we're going to talk about equilibrium, and we'll learn how to do a new type of problem that you have not seen before. Okay, so the first type of force that we encounter frequently in physics is the weight force. The weight force is simply the force due to gravity. Okay, and I'll denote the weight force by W, and it is equal to mass times gravity. Okay, so m is the mass of the object, g is the acceleration due to gravity at that particular location. So if this was on Earth, you would use g equals 10. It's important to emphasize the difference between weight and mass. Mass is an intrinsic property of an object. It's a measure of how much matter is inside that object, okay? Weight is the force of gravity acting on that, okay? So your weight can change from place to place. If you go to the moon, your weight force changes because the acceleration due to gravity changed. If you go to Jupiter, the weight force changes because the acceleration due to gravity changed. But your mass does not change, okay? Your mass is the same, provided you didn't, eat food or expel waste or lose a limb or something like that, okay? If we're doing a problem where the forces are all acting one-dimensionally, so maybe all the forces are horizontal or all the forces are vertical, then we don't really need to express the forces as vectors. Where vectors sort of come into their own is in 2 dimensions and higher. But if we did need to express the weight force as a vector, we could say weight vector is minus mg times j hat. Okay, so I've included the j hat to indicate that it acts vertically and the minus sign to indicate that it acts downward. Okay. The next force is the normal force. Normal force is also known as the reaction force. I know some of you are in my IB physics class. Some of you are in IB physics HL. And on the IB exam, they don't call it the normal force. They call it the reaction force. So you should just be aware of that. I will call the normal force F sub n. I think the IB exam calls the normal force R for reaction. Okay, so the normal force is the force preventing an object from passing through a floor or a wall or any solid surface, okay? So we're going to do a couple examples with the normal force here, okay? First example is really simple. Let's just say you have a flat surface and you have a 5 kilogram box sitting on that surface, okay? And that's it. Well, if we think about the forces that are acting on this, by the way, the normal force always points directly perpendicular to that surface. So I'll put that in parentheses here. Perpendicular to the surface. So the weight force acting on this 5 kilogram block is going to be m times g, so 5 times 10, which would be 50 newtons. And then the normal force points directly away from the floor, so that would be upward. All right. Now, so it turns out that the normal force in this case would have to equal 50 newtons. Why? Because what if the normal force was less than 50 newtons? In that case, you would have more downward force than upward force, and so the box would accelerate through the floor, okay? If the normal force was bigger than the weight force in this case, then there would be more upward force than downward force, and the box would fly into the sky. So the only thing that makes sense to have the box actually stationary on the surface, sitting there, is to have these two equal to each other, okay? So what you'll find is that oftentimes normal force is equal to the weight force, okay? But there are many scenarios where normal force is not equal to the weight force, and we're going to go over some of those right now. One example would be, so we're going to stick with this 5 kilogram box. Okay. And let's suppose that someone is exerting a 70 Newton force at an angle of 30 degrees above the horizontal. Okay? So we could think about that 70 Newton force as being two forces. One of the forces is going to be vertical, the other force is going to be horizontal. So the vertical component of this force would be 70 sine of 30, which is 35 newtons. And the horizontal would be 70 cosine of 30, which is 61 newtons. So we can think about this 70 Newton force at an angle as a 61 Newton horizontal force and a 35 Newton vertical force. And then we still have the weight force going downward, which is 50 newtons. And we still have the normal force going upward. Okay? Because the normal force points away from the surface, perpendicular, so that would be up and down. So notice how the 61 newtons is pulling the box along the surface. So the normal force doesn't care about that at all. Okay? This force might as well just not be there because it's not impacting the normal force. It'll cause the box to accelerate sideways, but it won't affect our normal force calculation here. Okay? So you can see here that the normal force must equal 15 newtons. Why? Because that would make the total upward force 50 newtons, which would balance the downward force. Okay? So this is an example where normal force is different from the weight force. Let's do another one. What if you have a vertical wall and you have a 5 kilogram block and it's being pushed into the wall with a 10 Newton force? What's going to be the normal force there? Well, we've got, which way does the normal force point in this case? Well, away from the wall would be the leftward direction. So the normal force is pointing this way. Okay, we've got 10 newtons going this way. And then we got 50 newtons going down. Notice how the weight force isn't playing any role in pushing this block into the surface. Okay, it's the 10 Newton force that is pushing the block into the wall, not the 50 Newton. Okay, so in this case, these two forces have to be equal, and the normal force is just 10 newtons. Okay, so if you have a wall, the normal force is not going to be equal to the weight force in general. Okay. Another example would be if you're in an elevator and the elevator is accelerating upward. In that case, the rider of the elevator has a downward force, mg, and an upward normal force. And the normal force has to be bigger in size than the weight force in this case. Why? Because if the normal force were bigger is not bigger in size, then the person cannot accelerate upward. All right? So the only way that the person can accelerate upward with the elevator is if normal force is greater than weight force. So I've just given 3 examples where normal force is not equal to the weight force. So please be careful about just assuming that that's going to be the case. All right. The next force I want to talk about is friction. Friction is typically denoted Friction is typically denoted by a script F, like on a violin or something, or in a cello. And it is the force preventing objects from sliding. Or I shouldn't say preventing, because it doesn't always succeed. It's the force resisting objects sliding across one another. Okay? The force resisting objects sliding across one another. There are two types of friction. All right? Two types of friction. The first type of friction is called static friction. And the second type is called kinetic friction. So here's the idea. Friction is present. Here's my desk. Friction is present if I push on the calculator, whether it's moving or not. Okay? If I'm pushing on the calculator, which I am right now with a very weak force, there's friction resisting my push. If I push hard enough that the calculator actually moves, there's still friction. Okay? So static friction is the friction that prevents or it's the force that must be overcome to make an object budge. Okay? We have an excellent question. For the box against the wall here, is the box falling downward since there is no friction, upward reaction force shown? Yes. So this is something where, so for this example right here, because there's no upward force fighting the 50 newtons, the box is going to accelerate downward. So this is kind of like you're pushing it against the wall, but you're not pushing, and it's sliding while you're pushing it against the wall. So I should use this one. So it's kind of like this. It's sliding downward while you're pushing it. Okay, so static friction is the force that must be overcome to make an object budge, to make it start to move. Kinetic friction is the force overcome to keep an object sliding. Okay? So we denote static friction by F sub S. We denote kinetic friction by F sub K. So there's a formula for kinetic friction. Okay? And it is mu sub K times the normal force. Mu sub K is called the coefficient of kinetic friction. And it is basically a measure of how rough the surface is. If the surface has a large coefficient of kinetic friction, then it's difficult to slide something across that surface, okay? If it has a small coefficient of kinetic friction, it could be considered frictionless. Notice how friction depends on the normal force, okay? Think about this. If you have your hands and you rub them across each other, it's pretty easy to do. I'm overcoming kinetic friction right now. But what if I push my hands together and then I try to slide them? It's more difficult. Why? Because by pushing my hands together, I have increased the normal force. Okay? So increasing the normal force increases friction. There's an analogous formula for static friction. Static friction goes up to a certain maximum value. Okay? And that maximum value is mu sub s times normal, where mu sub s is the coefficient of static friction. Now, generally speaking, mu sub s and mu sub k are not equal to each other. What is typically observed is that the force required to start something moving is more than the force required to keep it moving. You might notice this. If you try to push something, it's like once you get it moving, it jumps, and then it starts to slide evenly because you overcame static friction, which was greater than kinetic friction. So once it starts to move, it's like all of a sudden you're like, whoa. It budges suddenly and it accelerates forward. Okay? Let's do an example. We've got a flat surface. We've got a box, 5 kilogram box. Okay? It's on a flat surface. All right? So, and there's no other vertical forces. So we can say in this problem that the normal force is equal to 50 newtons, m times g. We'll say that the coefficient of kinetic friction is 0.5, and the coefficient of static friction is 1.0. All right? If you are sanding something, is that using static friction to remove the material? Yeah, I guess it would be static, right? It's kind of a combination of static and kinetic, but you are using friction to remove the material. Okay, so a person applies a horizontal force. I'm going to call that F sub A for applied. Okay? Notice that this F sub A is acting horizontally, so it's not going to change the normal force. If it was angled like this, it would change the normal force. All right? Let's go ahead and do these calculations here. What is the maximum static friction? The maximum static friction would be mu sub s, which is 1.0, times normal. Okay? So that would be 50 newtons. What's going to be kinetic friction? Kinetic friction is mu sub k times normal. So 0.5 times 50, 25 newtons. All right? So let's do two examples. What if the applied force is 40 newtons? What's going to happen in that case? Well, you need to apply at least 50 newtons to make something start to move. So if you only apply 40 newtons, nothing's going to happen. There's going to be no motion. This is, again, assuming that the block is at rest to start. Okay? If the block was already sliding, could 40 newtons keep it moving? Yes, because how much force do we need to apply to keep it sliding is only 25 newtons. Okay? But if we started with 40 newtons, it would never move to begin with. Okay. What if the applied force is 60 newtons? Okay. In that case, we overcome static friction. So it's going to start moving. Starts moving. And because it started moving, we are then going to have kinetic friction as opposed to static friction. Okay? So I could actually go to Newton's second law, net force equals ma. The net force is going to be 60 newtons pulling it to the right, minus the 25 newtons of friction resisting it. So 60 minus 25 would be my net force, and the mass is 5. So I could actually calculate the acceleration of the block. All right? Another force that we will encounter is tension, T, which is the force from a rope. And we'll come back to that later in the words of Forrest Gump. That's all I have to say about that. And then there is the elastic force, which is the force from flexing an object. Flexing, when I say flexing, I mean stretching or compressing. So it's the force that resists things flexing or stretching. So for example, if I have this notepad, I've got a notepad right here. And I push down on the notepad, it resists me pushing down on it. I'm flexing it downward, it resists it. I let go, it pops back. So that's an example of an elastic force. Of course, rubber bands, elastic bands, mattress springs, any kind of spring, those all exert elastic forces. So what is the formula for elastic force? F sub E for elastic equals Kx, where x is the so-called extension, and it is the amount stretched. Beyond taut. So I literally don't have any rubber bands in my house. So I was looking before giving this lesson. I couldn't find any. But if you think about a rubber band, it's flimsy. It exerts no force until the rubber band is completely pulled tight. And then if you go beyond that, that's when you start to get an elastic force resisting the stretching, okay? So if you have a rubber band that is 5 centimeters long, if you just put it on the table and it's 5 centimeters long, you're not stretching it. If you then pull it so that now the rubber band is 7 centimeters long, you went 2 centimeters beyond the natural length of the rubber band, the unstretched length, okay? So in that case, x would equal 2 centimeters. K is called the stiffness. Units of K are newtons per meter. And so rubber bands, shocks in your car, different springs have different K values, which is basically how difficult is it to compress or to stretch a material that flexes, okay? And I want to say that every material flexes, even if it's an imperceptible amount, because in order to exert, what if you're not flexing at all? What is the x value if something is not flexing? It is 0, okay? Everything flexes in order to exert an elastic force, okay? When you walk on the floor, in some sense, the normal force and the elastic force are the same thing, right? You're pushing down on the floor. The floor flexes downward a little tiny bit. If it's good construction, the amount that it flexes down is imperceptible, but it does flex downward. and that generates the elastic force that holds you up. Okay? Everything, even the most solid-looking structure. All it means if a structure is super solid is it means that the amount that it flexes under a load is imperceptible to you. Okay? But everything does flex, at least a little bit. Okay. So we're going to move on to the second topic for this lesson, which is equilibrium. And equilibrium means that the net force vector is equal to 0, which in turn means that the net force in the x direction is 0, and the net force in the y direction is 0. Okay? So the net force in the x direction and the y direction are 0. So if the net force is 0, that means that the acceleration is 0. According to Newton's second law, net force equals ma. If the net force is 0, then that means the acceleration has to be 0, which means that the velocity is constant. So an object is in equilibrium if its velocity is constant. Okay? So it means that the velocity is constant. Usually, that constant velocity is 0. When we're talking about an equilibrium problem. Okay? Structural engineers very often are solving equilibrium problems. Okay? And the velocity of the structure that they're analyzing is 0 because it's a building. It's not a moving building. It's a stationary building. So most of the time, the constant velocity is 0. So let's do an example. Let's suppose we have a ceiling. Okay. And someone wants to hang a sign from the ceiling. Here's the sign. It's a 50 kilogram sign, is the mass of the sign. And let's just say for simplicity, it's a mega sign. All right. The other day I was walking my dogs, and one of my neighbors has a big mega sign in front of their house that's hanging. And it's kind of like, oh, okay. Go you. And so anyways, the sign is supported by 2 ropes. One of the ropes is at a 45-degree angle. Okay. And interesting, this class is definitely the other class I had a MAGA sign as well, and no one reacted to my political to something political, but this class definitely strongly reacts to the politics. Interesting. And then there's a second rope that makes an angle of 60 degrees with the horizontal. Now these are ropes, so they exert tensions. That's tension T1, that's tension T2. Okay? And so what we want to do is determine what are the tensions. Okay? So we're going to use the fact that the sign is in equilibrium. So what I'm going to do is I'm going to draw what's called a free body diagram. I'm going to represent the mega sign as a dot, and I'm going to draw the forces that are acting on it. So there's force T2 at an angle of 45 degrees. And there's force T1 that is at an angle of 60 degrees. And then there's a weight force, which is 500 newtons. Okay? Notice that the mass is 50 kilograms. So I take the mass and I multiply it by gravity and I get 500. Okay? Now I'm going to go back and I'm going to take, one of the things you want to do in physics is you want to take any diagonal forces and you want to break it into components where it's a vertical and a horizontal force. So I'm going to redraw my free body diagram. The vertical component of T2 is going to be T2 sine of 45 degrees. The horizontal component is going to be T2 cosine of 45 degrees. Now, sine and cosine of 45 degrees are equal, and they're both equal to 0.71. So this angled T2 force is equivalent to an upward force that is 0.71 T2 and a rightward force that is 0.71 T2. Okay? Now let's turn our attention to T1. The vertical component of T1 is going to be T1 sine of 60. And the horizontal component is going to be T1 cosine of 60 degrees. Okay? Sine of 60 is 0.87, I believe. It's root 3 over 2. 0.87. So I can think about the T1 diagonal force as an upward force of size 0.87 T1 and a leftward force of size, cosine of 60 is 1/2, so 0.5 T1. And then I have the weight force, which is 500 newtons. So I've taken my diagram with diagonal forces and I've turned it into a diagram with all vertical or horizontal forces. Okay? That just makes it simpler to analyze. So the fact that this sign is in equilibrium means that the horizontal forces have to balance. Okay? There are two horizontal forces. So that means that 0.71 T2 has to equal 0.5 T1. If they don't, then the horizontal forces will not match, and it'll accelerate sideways. Similarly, the upward forces have to equal the downward forces, otherwise the sign accelerates up or down. So the upward forces are 0.87 T1 plus 0.71 T2. And those have to balance the downward forces, which are 500. Okay? So notice how I have so now I have two unknowns, T1 and T2, and two equations. So this is a system of equations that you can solve using whatever method you want to use. One method is to use substitution. So I could write, T2 equals 0.5 over 0.71 T1. I could then plug that in for T2, and then I could solve the second equation for T1 and then plug it back in. That's called Gaussian elimination. So I could use Gaussian elimination. Another method that I'm going to use is a graphical technique. Okay. So let me switch over to Desmos here. So you can see that on the vertical axis, I have T2, and on the horizontal axis, I have T1. So I'm going to simply type in the equations. So T2 is y, so I have 0.71 times y equals 0.5 times x. So that's my first equation representing force balance in the horizontal direction. Then I have my vertical equation, which is 0.87 T1, which is x, plus 0.71 T2, which is y, equals 500. Okay? And I can see that gives me two lines. Now, the solution is the point where both of these lines intersect, so I can go over the point of intersection. And I can see the x-coordinate, which is T1, is about 365 newtons. And T2 is 257 newtons. Okay? So that is a graphical way to solve these. Probably the best way is to use a calculator, because the graphical method only works if you have two unknowns. Okay? You also, another reason the graphical method might be tricky is if your window is off. Like, for example, what if this was my window? You know, what if that was my window? Then you have to kind of waste time figuring out where's the other line, where is the intersection. You know, zoom out, find it. So, you know, probably just learning how to do this on your calculator is the best method. Okay. So now, what if we said that the ropes can withstand 300 newtons of force? So when you buy rope, it has a certain maximum weight that it can hold. So if you go to Lowe's or Home Depot, you buy rope, and it'll say this rope can hold 25 pounds. Okay. So what if these ropes can hold 300 newtons of force? In that case, well, T1 is greater than 300. So T1 is going to snap. T1 snaps. Then the sign is now going to swing down vertical, so maybe it's going to look kind of like this, maybe. Okay. And now T1 is bearing all the weight of the sign, or T2, excuse me, is bearing the entire weight of the sign, which is 500 newtons. So then T2 is going to, so once T1 breaks, T2 is going to eventually become 500 newtons, which is also greater than 300. So that rope is going to break, and then the sign falls. Okay? This is an example of, of a cascading failure. So there's a way something can fail. It's called a cascading failure. It's where one part fails, and then because that one part is not doing its job, all the other parts have to pick up the slack, which increases the stress on the other parts, which then makes another one fail. Now the remaining ones are bearing even more stress, so you get just this cascade of failure after failure after failure after failure, and then the entire thing very quickly just falls apart. Okay? So that's my lesson for today. I hope you enjoyed, and I will see you in the Zoom room.